Okay, so this is 12.2, and we're looking at more examples of the percent change in exponential functions. So take a look at this example. They have an account that contains $2,000. It decreases in value by 20%. So they want you to find the decrease in value of the account, and then find the final value of the account, and then by what factor did the account decrease. So for A, so we say that A is 2,000 because that's what we started with, okay? And R is our interest. It's decreasing because it said it decreased, so it's negative 0.2 from the 20%. So if we multiply the two, we get a negative 400. So the account's going to decrease by $400. The final value of the account is to take the original and minus what you're going to lose, so you get $1,600. And then the account decreased by a factor of 1 minus that rate, so about 80% is the decrease on that. So we're going to do problem 57, but before we do that, here in general, a positive amount of A cannot decrease by more than 100%, because then it would go down to 0, and you can't have that because you always have to have some amount. However, percent increases can go more than 100%. So that's just a note to keep in mind. Also, percent change in exponential functions. An exponential function, and we'll talk about that next. But let's go to that particular page. Let's do 57. So 57 is on 836. So 836. And we look at 57. So here is 57 down here. Okay. So for each A and R, answer the following. Find the increase or decrease in the account, the final amount, and by what factor did it do it. Did it increase or decrease? So A is going to be 100%, and R looks like it's positive, so it's going to be an increase. So let's go to my workspace. Okay. And so for 57, they said A is going to be $1,000, and that R is going to be 120%. And we're going to change that to decimal, so we're going to move it 2 places. So 1.2 is what we're going to do, is for the setup. So to do that, we're going to take the R times the A to figure out what that increase is. So we take 1,000 times 1.2, and so on our calculator we're going to get, we're going to do 1,000 multiplied by 1.2, so we get 1,200. So we're looking at 1,200. Okay, so that would be our account increase. So this is an account increase. Okay, and then the final value would be to take this amount, because that's the end, and then add it to the amount that we have. So that would be the A plus the actual amount, which is 1,200. So we're going to get $2,200, and so that's going to be our final value. Okay, and then we want to know the amount increase. That's basically A equal to R plus the 1, right? So that's 1 plus the interest, right? And so we get 2.2, and if we multiply that by 100, we get 220%. Okay, that's what we're looking at as an increase, okay? Because we're taking the 1 plus the 1.2. And so this is the setup for that particular problem. Let's go back to the book. Okay, and we'll go back to page 829. Okay, and we want to look at the basic generic form that we've been just doing, which is percent change in exponential functions. So R's always got to be uh, positive. That's why it's greater than 0 here to be a growth factor. Okay, and if it's less than negative, if it's -1, but it can't be -1, but it has to be between this, then we know it's to decay. So it would be the A equal to the 1 plus R. Okay, so if the initial amount of C is our amount and A is is the amount after the x units of time is given, we have these two particular equations. So we have C times A to the x, or we have that interest for increase or decrease. So we can write it as well as this way. So take a look at analyzing growth of a bacteria. So a laboratory culture contains 50,000 bacteria per millimeter. It's increasing in numbers by 20% per hour. So I want you to write a formula, an exponential function form for this, and evaluate it for B to interpret your results. So we're going to let our start number be 50,000 for C, and then our increase is 20%, so we change it to decimal point 2. And so now the growth factor would be 1 plus the 0.2, which is 1.2. And so we put it into our equation of 50,000 times 1.2 to the x. So this would be our final equation. And then we would put 3 into the equation to see how many bacteria there is. And so we would do the 1.2 to the third and then multiply it by 50,000. So you get about 86,400 after 3 hours. That's how much bacteria per milliliter. So let's do 87. So let's go to page 837. So I'm going to go to page 837. We're going to look at problem 87. So it says write the formula for an exponential. Here's the equation that models the situation. So a sample of 5,000 bacteria, but this time it's decreasing in number by 25% per week. So let's write that information down. So for 87, we have the formula of f of x equal to c times a to the x, where they say that C is going to be 5,000 bacteria, and then we're going to have a decrease of about 25% per week. Okay, so that's the problem that we have, and they want us to evaluate at 4. So we're going to have x equal 4 and when we get done with this formula. So let's take a look how we're going to go about doing this. So we do know A is going to be 1 plus, and since it's decreasing, it's negative 25%. So that's 1 minus 0.25, which turns out to be 0.75. Okay, so there's the 0.75 for A. Okay, and I already know what my start is, so I'm going to use f of x equal to 5,000 times 0.75 to the x, and then I'm going to put 4 in. So f of 4 is 5,000 times 0.75 to the 4th power. So now I'm going to go ahead and put that into my calculator. Right, so I'm going to do 0.75 to the power of 4, and then I'm going to multiply that by 5,000 because that was my start number, And then here's my answer. It's 1582 is what I get. So 1582 is my result for this. And so 1582 is the amount of if it was bacteria that decreased. So this is the decreased value that it will have over 4 hours or 4 weeks. And so these are the basic problems for doing these kinds of problems.